In our previous series of lesson videos on the probability calculus, we learned a rule for determining the probability of a conjunction. But that rule was limited. It only applied when the conjuncts were independent. So this lesson is going to introduce a general conjunction rule. But first, since we can no longer assume independence, we're going to find out a way of determining independence. So the goals of this lesson are figure out how to determine whether statements are independent, and we're going to use information about their conditional probabilities to do so. And then we're going to define a general conjunction rule and look at an example of how to use it. Remember that two sentences are independent if the probability of one doesn't vary with the probability of the other. So far, when we think about independence, we've relied on intuitive judgments. Things like our knowledge of facts about the world. For example, we intuitively know that 2 dice rolls in a row are independent because there's no reason to think that the number that rolls the first time will have any impact or relation to the number that rolls the second time. But sometimes we can't easily or automatically determine whether statements are independent. Are heart disease and higher than average weight independent? It's not immediately obvious whether they are or not, and conditional probability can help us make that determination. We're going to contrast independence with dependence. So statements are dependent if their probabilities vary together. It's important to note that when statements are dependent, that doesn't mean that the probability of one statement causally affects the probability of the other statement. Dependence is capturing correlation and not causation. So let's go back to our heart disease example. If we find that heart disease and higher than average weight are not independent, that doesn't tell us that higher than average weight causes heart disease, or vice versa. It might be that some further factor causes both of these conditions and explains the dependence relation. If we need to determine whether statements are causally related, that requires some further reasoning, and we'll look at that more in future lessons. What we want now is a formal test for whether or not 2 statements are independent. And we can get one by using conditional probabilities. So if we take the probabilities of P and Q that are greater than 0, so there has to be some chance of P and Q being true, those 2 statements are independent if and only if they meet this condition. The probability of P given Q is equal to the probability of P. Otherwise, the statements are dependent. So what does this mean? The probability of P when Q is true isn't affected by the truth of Q. So it's equal to the probability of P. That makes sense when we think about independence. There shouldn't be relations between the probabilities of the statements being true. If the probability of a statement P is the same as the conditional probability of P given some other statement Q, then the statements are independent. And note that independence is what's called a symmetric relation. So it always holds in both directions. If P is independent of Q, then Q is independent of P. And that's why it's in general better to just say P and Q are independent of each other. It's also important to know that if P is independent of Q, there is no relation between the truth of P and the truth of Q, and that should apply to the probability that Q is false as well. So when the probabilities of P and not Q are non-zero, the probability that P is true should also be independent of the probability that not Q is true. If P is independent of Q, P is also independent of not Q. Now we just showed that P and Q are independent if P given Q, that probability, is equal to the probability of P. We can also show independence just as well by showing that the probability of Q given P is equal to the probability of Q. So whether we appeal to the probability of Q and Q given P, or the probability of P and P given Q, is equally good, but we have to pay attention to getting the right order. Now we're going to look briefly at a proof of why both of these versions of the formal rule for showing independence work. And the benefit of going over this informal proof is that it helps you see how we can use basic algebra to rearrange some of our probability equations and to see the relationships between different probabilities. So the probabilities of conjunctions, conditional probabilities, the probabilities of simple statements. It's important to be able to manipulate these formulas because it can be valuable in solving various probability problems. So here's how the proof goes. We start with our definition of conditional probability. So remember from the last lesson video, the probability of P given Q is defined by the probability of P and Q divided by the probability of Q. That's just the definition of the conditional probability P given Q. Now we've just been given this extra fact about independence. When P and Q are independent, the probability of P given Q is just equal to the probability of P. So that lets us substitute. When P and Q are independent, the probability of P is equal to the probability of P and Q over the probability of Q. Now we want to focus on the probability of Q and eventually show that it's equal to the probability of Q given P. So to focus on the probability of Q, we need to rearrange our equations slightly, and that just requires some basic algebra, multiplying probabilities and dividing by probabilities. And now we have the probability of Q is the probability of P and Q over the probability of P. But if you take our conditional probability formula, that fraction on the right there, that just is the definition of the probability of Q given P. So that tells us the probability of Q given P is the probability of Q. So since we can derive this version of the independence rule from the other one, that shows that they're equally good. And we did so just by a series of equivalences. Now previously we had a simple conjunction rule that took advantage of this property of independence that we've just spent time looking at. So we know that if P and Q are independent, we get a simple formula for the probability of the conjunction of P and Q. So Rule 7 told us how to calculate a conjunction on the condition that P and Q are independent. We can just multiply the probability of P with the probability of Q. But what if that condition doesn't hold? What if P and Q aren't independent? Or if we just don't know whether they are or not? We want to know the probability of a conjunction regardless of whether P and Q are independent. So that's why we need a general conjunction rule, one that applies regardless of the independence of P and Q. That's our Rule 10. For any two statements P and Q, the probability that the conjunction P and Q is true is equal to the probability of P given Q times the probability of Q. So again, that's how we determine the probability of a conjunction if we don't know whether or not P and Q are independent. How can we motivate this new general conjunction rule? Well, what we need the rule for is we need to know the probability of both P and Q being true, and we need to know that probability when the probability of Q being true can be related to the probability that P is true. So the probability of the conjunction P and Q is the probability of falling in the overlap of the circumstances that make both P and Q true. That's the same as with our simple conjunction rule. The difference now is that how likely they are to both be true together depends on how their probabilities co-vary. So what's the chance of them both being true? First, we have to account for how likely P is to be true if Q is true. That's the conditional probability. And then we have to account for how likely Q is to be true in the first place. In terms of the Euler diagram, we have to use not only the ratio of the region where P and Q is true to the size of the Q region. That was our conditional probability, if you remember. We also have to figure out how big the Q region is relative to the whole space. So the size of the overlap is determined not only by the ratio of the P and Q region to the Q region, but also how big that Q region is in the first place. Only then can we say how likely we are to fall within that overlap of circumstances where both of these sentences are true. Now let's go over an example of how to use this general conjunction rule. This example draws loosely from one in the Weisberg text, but it's a little different. So imagine you're doing a cooking challenge and you're required to draw a random ingredient. And this is how you're going to draw it. There are two bags, A and B, and in each of the bags are ingredients named on slips of paper. Bag A contains 4 savory ingredients and 1 sweet ingredient. And bag B contains 4 sweet ingredients and 1 savory ingredient. So there's a mix of ingredients named on the slips in both. And the way your draw is going to work is as follows. First, you have to flip a coin to determine which bag you draw from. So if it's heads, you draw from A. If it's tails, you draw from B. And then you reach into the bag and randomly draw a slip of paper from that bag. You should already get the feel that whether you end up drawing from bag A or bag B is going to have an impact on how likely you are to draw a savory ingredient or a sweet ingredient, since savory ingredients are more likely in bag A and sweet ingredients are more likely in bag B. Now we can ask the following question. What's the chance you draw from bag A and pull a sweet ingredient? To determine this, we can use our general conjunction rule. So the relevant possibilities to this example can be given with the following sentences. We'll have A as you draw from bag A and B as you draw from bag B. That's the part that depends on the coin flip. And then once you reach into one of the bags, either V is true, you draw a savory ingredient, or W is true, you draw a sweet ingredient. Remember, the question we're interested in is what is the chance you draw from bag A and pull a sweet ingredient? So we're looking for the probability of A and W being true, that conjunction. Because the bag you flip for impacts how likely you are to get either type of ingredient, we need to use our general conjunction rule. And we need to use this version. The probability of A and W is equal to the probability of W given A times the probability of A. So we could, in principle, get this probability by switching W and A. But we don't want to do that because we know that the probability of W depends on the probability of A. So we want to use the version that has the probability of W given A as part of the formula. And we also know that the probability of A is independent. It's just what do you get from a single coin flip. Of the possibilities listed above, we're only going to need to worry about A and W, drawing from bag A and drawing a sweet ingredient. So with this formula, we can determine how likely a slip of paper in bag A is to have a sweet ingredient on it. Since drawing from bag A or bag B is determined by a simple coin flip, they have equal chances. Then our question is, if we're drawing from bag A, how likely are we to draw a sweet ingredient rather than a savory one? So we can ignore bag B. Now we were told that bag A contains 4 savory ingredients and 1 sweet. So the chance of getting a sweet ingredient, given that we're drawing from bag A, is just 1 in 5. And with that, we have everything we need to know to get the probability of drawing from bag A and getting a sweet ingredient. We know what formula we have to use and the probabilities we need to substitute into it. So now we just have the substitutions left. 1/5 is the probability of the ingredient being sweet, given that we're drawing from bag A, and 1/2 was the probability of drawing from bag A. And it turns out that the probability of both of these statements, A and W, being true together is pretty low. It's just 0.1. That should make sense, given that there aren't many sweet ingredients papers to pull from in bag A. The general conjunction rule is the last of our rules for determining the probability of complex sentences. But our next lesson video will show us one last rule from the probability calculus, one that pulls together the relations of the probabilities of simple sentences to the probabilities of complex sentences, by showing how the probability of a simple sentence can be determined from other probabilities.